Okay, hi everybody. It's New England Dynamics and Number Theory seminar again, and we're happy to hear today Soffer Aranov from Israel, from Technion, telling us about covering radii in positive characteristic. Thank you, Noy.
Hi, thank you very much for the organizers for this opportunity, especially at such crazy times. I'm very grateful to be able to give a talk in the seminar. I've been a participant here since 2020 when this started at COVID times, and I've really enjoyed the seminar since, and I'm very happy to give a talk here. So I'll tell you a little bit about this. What this is about my PhD research in covering radii in positive characteristic. And since the PhD is about to end, actually, in the middle of 2024, then I am actually looking for a postdoctoral position starting fall of 2024. I'll just start with that note. And now let's get to the math. So firstly, let me explain what's a covering radius. If we have some function f, which we wanted to have some nice properties, like it will be from Rd to the positive real numbers, the non-negative real numbers, and f at 0 is 0. And we have some unimodular lattice. That is a lattice of the form GZD, where G has determinant 1. We define the covering radius of lambda with respect to f to be the infimal R such that if we increase R slightly, and we take the set of all the V's such that f of V is less than or equal to R, and translate this set along all the lattice points of lambda, then we cover the entire space Rd. This is a little hard to understand without a picture, so let's see this in a picture. For example, here, let's take the lattice to be these pink points, which is the standard lattice, ZD, or in this case, Z2. And we're going to take f to be the function given by the L2 norm. Over here, this blue circle is a set of v's such that f of v is less than or equal to 1. In this case, that's R. And we ask by how much must we expand or contract this circle so that if we center it around every one of these pink lattice points, then we will cover absolutely everything. So as it turns out, the correct contraction ratio here is going to be 1 over square root 2. And we can see in this picture that if I center around all these lattice points balls of radius 1 over square root 2, then we cover absolutely everything. And moreover, this radius is minimal in the sense that if I decrease this radius slightly, then we will have these gaps. In particular, if you take these points here, then if we decrease all these radii slightly, then you'll have gaps around these points here, depending on how much you decrease these radii. And this is what I mean by this covering radius here. So this is an example of a covering radius with respect to a convex body. Let me explain what this means. We have some convex body C with non-empty interior. In the previous case, there was the L2 ball. And now the covering radius of lambda with respect to the convex body C is the infimal R such that if we take the shape R times C and translate it along lattice points of lambda, then we cover the entire space Rd. Now, how does this connect to our previous definition? It connects because these convex bodies induce a norm on Rd, which is given by the norm of V with respect to this convex body C is the infimal R such that V is a point in R times C. Now, one can check that this has all the natural properties of the norm, and moreover, the covering radius with respect to C of lambda is the covering radius with respect to the C norm of lambda. Now, one trivial example that we could have in mind for this is if we take any norm, then the convex body, which is going to be given by the radius 1 ball with respect to that norm, induces that norm. So that's why this definition is natural in a way. Now, we can see that covering radii with respect to convex bodies, they're proper functions. And one way to see that they're unbounded is in the following sense. For instance, if I take, let's go back here, if we take this here, and let's say we change this lattice by, for example, we want to take, instead of these points here, we're going to take this here and expand it by a lot. And then we contract this by a lot. And then after that, we'd need especially large balls in order to cover this type of a lattice where it has this point and this point, and these points here, for example, as being its fundamental domain up to my drawing abilities. Okay, So that's one way that we could see this, that it's unbounded. But now we can ask about the lower bound of this, if we take unimodular lattices, for example. So let's talk about some known results. These have been studied very well, these type of covering radii with respect to convex bodies. And one early result is from Rogers from 1959, which says that if you take the infimum over unimodular lattices of the covering radius with respect to a convex body C of some lattice, then we get that it's going to be of order of d to the power of a log 2 of log d. A recent result from 2020 by Ordentlich, Regev, and Weiss shows that this exponent can be improved too. So maybe this is a bit hard to think about this infimal covering radius, and let's try to work with an example. So if we take, for example, the covering radius with respect to the L2 norm of the standard lattice ZD, then this should be square root d over 2. And this is a not so difficult computation, and as we saw in our previous example where d was 2, this indeed fits. So now this may be a good time to ask if anyone has any questions. And of course, if during the talk you have any questions at all, please feel free to stop me and ask. Okay, if there's no more questions, then
just a question. So ZD is the lattice that realizes the infimum for Euclidean norm?
Yes. That d in this case, this is the Euclidean norm, the L2 norm.
No, but I'm saying that this square root of d over 2 is really the infimum.
Yes, it is.
Okay.
Yes, this is indeed the infimum. That is, it's going to be the smallest where you can cover everything. That's why it's the covering radius. Okay. Now we can ask what happens when we take covering radii with respect to other functions which are not induced by convex bodies. And for this, there's, of course, many different functions that we can take. But since this is a dynamics and number theory seminar, then I would like to take a function which is dynamically interesting, and I'll explain shortly why. So the function that I would like to take is I'd like to take the function f to be the product of the coordinates of a vector v in absolute value. And we define the Minkowski function mu to be the covering radius with respect to this function f. So now we want to cover by these shapes here of this form. And an alternative way to see this, if you don't like this geometric definition of a covering radius, is to say that the covering radius mu of lambda is going to be for the supremum over v's. For every v, you take the u such that you can approximate v with respect to u in the lattice best with the function f, and you take the worst possible v in this case. So that's a different way of looking at it. Now, let's see how this looks like. So in this case, these lines here, the star, everything within these lines, which we call a star, is going to be the set of v's such that the product of the coordinates is less than or equal to r. And we can ask, what arc should we take so that if we move this along all these lattice points, we cover everything? And what's going to be the nicest, smallest r that does this? So now let's talk about how does this have to do with dynamics. The main connection to dynamics is that mu is invariant under the group of diagonal matrices with determinant 1, which we denote here by A. And moreover, we know that A acts ergodically on the space of unimodular lattices. Sorry, is there a question? Is there a question? I'm sorry. Okay, I'll go on then. So since A acts ergodically on the space of unimodular lattices, then we know that mu must be constant almost everywhere. And one question is, what is this generic value? And one of the results that my advisor Uri Shapira showed in his PhD thesis is that this generic value is 0. That is a different way to interpret it, is that you can approximate multiplicatively well almost every point in this lattice. I'll explain that shortly. And now we can ask about what is the set of all values that mu obtains. So it's kind of difficult to say, I'm going to go over all of the possible lattices in XD and I'm going to compute mu for them. That's very difficult. But since we have this A invariance, we can take a much smaller set. In particular, we say that if Y is some subset which intersects every single A orbit, then we can obtain the set of values that mu obtains on all of XD. Is going to be the same as the set of values that mu obtains on Y. That is, to understand mu on the entire space of lattices, it suffices to look at mu on some set Y which contains a representative of every A orbit.
Yeah,
and
so
by the way, yes.
Very, very sorry. Can you repeat what is mu? I just forgot. Is it the covering radius with respect to?
Yes, mu is the covering radius with respect to this multiplicative function.
Okay, thank you.
So this can make things easier. And now from here, we can ask, for instance, maybe we don't want to calculate the entire set of values because that is a bit difficult. We have the generic value, which should be the lower bound because covering radii are always non-negative. And now we can ask, what is the upper bound, if there even is one? So I'll discuss that soon, what's the upper bound. But before that, I would like to talk about a different approach to this, which is, this is dynamics and number theory seminar. So I'll talk about a connection to Diophantine approximation. So one way to view this in the sense of Diophantine approximation is as an inhomogeneous version of Littlewood. So here, most of you know of Littlewood's conjecture, which says that for every theta and phi, the infimum. I'm sorry. Is there a question? Okay. So Littlewood's conjecture says that the infimum for all theta and phi, for of n, where n is in n, of n times the distance of n phi from the whole numbers times the distance of n theta from the whole numbers should be 0. Now, it's clear that this would hold for any theta or phi which are well approximable, and therefore it should hold almost everywhere. The best result towards Littlewood's conjecture is a seminal paper by Einsiedler, Katok, and Lindenstrauss, which says that this holds for outside of a set of Hausdorff dimension 0. Now, what does this have to do with the Minkowski function? So one way to view this is that I said that the Minkowski function is in a way an inhomogeneous version of whatever you see here in Littlewood's conjecture. So let me take, for instance, this lattice here, which you could view it in the following manner. You have here ones on the diagonal, and then the last row is going to be theta, phi, and 1. So also you could do a high dimensional version. This is basically ID, and then here you put some vector. Here this is going to be some vector, and here this is going to be ID if you want it in high dimension. Now let's compute this lattice's Minkowski's function. We can compute this and find out that the Minkowski function on this is going to be exactly what's written here, which is you take the supremum on alpha, beta, and gamma and for every one of these, you take the infimum of n on n plus gamma times the distance of n theta plus alpha from the whole numbers times the distance of n phi plus beta from the whole numbers. Now, this looks a whole lot like what we see in Littlewood's conjecture, but an inhomogeneous version. And we can view this supremum as saying, what is the worst possible shift that I can approximate with respect to this function? So one way that we could reinterpret in this sense Shapiro's result is we could say that his result says that for almost every theta and phi, the worst possible shift with respect to this Littlewood, the worst possible inhomogeneous Littlewood shift is going to be 0. So you could say that this is like saying for almost every theta and phi, the inhomogeneous version of Littlewood holds. Now, as we saw, we don't think that this should hold for every single theta and phi. And moreover, we can discuss the worst shift in a way. And this is the upper bound of the Minkowski function. And this goes back to a conjecture by Minkowski, which says that for every unimodular lattice, firstly, we have that the upper bound is going to be bounded by 2 to the power of minus d of mu, and moreover, this is going to be equal to exactly mu of zd. the fact that it's equal to mu of ZD is a simple computation. And also we can ask, so what values obtain the upper bound? The second part of Minkowski's conjecture says that this upper bound is unique to the A orbit of ZD. Now, this conjecture has been proved for D, which is less than or equal to 10, and some of the proofs for very low dimensions, like 2 and 3, date back to Minkowski and I think Dyson or Rimac, which are very, very ancient proofs from about 100 years ago. And there's even some more modern proofs for dimensions 9 and 10 from, I believe, 2020 and 2022 even. But there has not been a method to do this in every single dimension. So now I can discuss a little bit about my research, which is which is what happens to this whole story when we replace this with the function field setting. And what are a few motivations to do this? So one motivation to do this is, as I said, this Minkowski's conjecture, we could not prove it in every dimension in R, but maybe we can do it in this function field setting. So that's one way to view it. Another motivation that we have for this is that the function field setting is the correct positive characteristic analog of R. And in general, it's nice to understand this positive characteristic analog and to compare the differences and similarities in these two worlds of positive characteristic and real. So in this case, instead of R, we're going to use K tilt, which we denote by which is going to be the function fields. That's going to be the Laurent series. That's going to be the set of all series of the form sum an x to the n, where an is going to belong to a finite field fq, and we could have possibly infinitely many negative powers, but at most finitely many positive powers. Now, for those of you who do not have an intuition on this, you could think, if instead of x, I put q, then I get exactly r. I just get the quinary expansion of items in R. So now let's understand who are the players in this world. I'll put a chart and I'll explain it shortly. So firstly, instead of integers, z, our integers are going to be polynomials. That is, we have no negative powers, but at most finitely many positive powers. And this fits well with the analog of if I put there q instead of x, then I get exactly z. Our field instead of R is going to be this Laurent series, and we need an absolute value since there is some geometry here when we talk about these covering radii. So our absolute value is going to be q to the power of the degree of the Laurent series. That is the largest power that we see there with the non-zero coefficient. And the norm, if we have some vector, then the norm is going to be the infinity norm. That is the norm, if we have some vector v, then the norm of v is going to be equal to the maximum I of the absolute value of the coordinate vi. And the standard lattice, instead of our usual zd, is going to be rd. That is the set of vectors in Laurent that have only polynomial coordinates. And our space of lattices is going to be all of the items of the form g times rd, where g has determinant of absolute value 1. And we denote the space of lattices over k tilt by ld. Now, I'll show you a little bit about how this k tilt looks like, and this unique geometry is going to enable several of our results. So one way that we could view the geometry of k tilt is in the following manner. So we have here all of these spheres. For example, this sphere here is going to be the sphere of all of the points which have degree 0. That is all the elements of the form of this form, n equals 0 till infinity of a n x to the minus n, where a0 is non-zero. And then these ones all have absolute value q. These ones all have absolute value q squared, and so on and so forth. And we can see that as we go to infinity, these spheres, they get increasingly sparse. And on the other hand, as we go to 0, these spheres, they get increasingly dense. One way to say this is that the only element that I can converge to along different spheres is 0. That is, if I want to converge, for example, to this point here, eventually, I will have to take points that are on this specific sphere. But 0 is the only point that I can converge to along different spheres. And this is one of the unique aspects of the analysis here, which helps it make some of the computations easier. Now let's see how this looks like. Another way to view this is that around every single non-zero point, there exists a ball with respect to the absolute value, which is all contained in its sphere, as we can see here. So this unique geometry will enable many of our results. So now that we understand a little bit about the space, we can talk about covering radii in the setting, unless if somebody has some questions about this space here. Okay, then if there's no questions, I'll continue. So let's talk about covering radii in this setting. So now we have f, it's going to be this time a function from k tilde to the positive reals, to the non-negative reals, and we still want f of 0 to be 0. And if we have some unimodular lattice, or in general any lattice, but let's take only unimodular ones for right now, then we define the covering radius with respect to f of lambda to be the infimal r, such that if we increase it slightly and take the set of points v in k tilde such that f of v is less than r, and then we translate this along lattice points of lambda, then we cover the entire space. Now, let's see an example. One simple example is going to be f is going to be the infinity norm. So now this is actually a covering radius with respect to a convex body. In this, I haven't yet defined it yet, but we're going to do things a little backwards now. So in this case, this is the covering radius with respect to the convex body OD, where O is going to be the maximal order. That is, it's going to be the set of all of these, of all of the Laurent series that are of this form here, that they have norm at most 1. That is absolute value at most 1. That is, they only have non-positive powers. Now let's define formally what is a covering radius with respect to a convex body. Before we do that, we have to define what's a convex body, because the thing is that most of us know the definition of the convex body being that every single line is contained in the space, in the set, but in this case, the geometry is very different, so we don't really have the notion of lines. But as it turns out, the correct notion of a convex body would be that if u and v are going to be in our convex body C, and alpha and beta are going to be in O, then we would like alpha u plus beta v to also be in C. So using this notion of a convex body, which should be the natural thing, it turns out that it was proved by Mahler that every convex body would be in the form of H times OD, where H is some invertible matrix over K tilde. So this actually helps things be a lot simpler, because convex bodies are simply linear pictures of the unit ball with respect to our norm. And now we can define what's a covering radius with respect to a convex body. So if we have some convex body, we define the covering radius with respect to the convex body C to be the infimal r, such that lambda plus RC is going to be equal to K tilde to the D. Now, because of this very simple form of convex bodies, I was able to prove during my PhD that if we have some convex body of the form H times OD, and we have some lattice, not necessarily unimodular, any lattice, then the covering radius of lambda with respect to C is going to be equal to 1 over Q times lambda D of H minus 1 of lambda, that where lambda D is the D successive minima of our lattice H minus 1 lambda. So let's discuss firstly what the successive minima is. So we know we know the following. If we have some lattice, then we can define the I successive minima to be the smallest r, such that lambda contains I linearly independent vectors of length at most r. Now, if you take lambda 1, that is simply the length of the shortest non-zero vector. And we could view it geometrically as simply taking balls, if this is the center, then we can simply take balls and we can ask, when do I have inside of this ball I linearly independent vectors? And that's how we could view this geometrically. And now one thing that we know is Minkowski's second theorem. It connects between the product of the successive minima and the volume and this determinant of G. Now, in this case, in the real case, we know that it's a double-sided inequality. In positive characteristic, one remarkable property is that the determinant of G in absolute value is actually equal to the product of the successive minima. This is one of the things that enables our proof. Now, because of this, there's another very remarkable property in positive characteristic, which will not be true in the real sense, which is that for every lattice, we can find an R basis of successive minima. That is, we can write lambda to be equal to R times V1 plus R times VD. And by the way, this property, though it may seem natural, is not true in the real setting. And this is one of the things that enabled many of our proofs here and enabled this very simple form of the covering radius here, whereas in the real case, it's not so simple. So let me give a counterexample in the real setting. Let's take, for example, this lattice here, which is going to be equal to it's going to be the lattice that has coordinates which are all either even or all odd. And one way to view this is as being this 2z to the d plus z times vector 1, 1, 1, 1, 1. Now notice that if we take d, which is at least 5, then the set of shortest linearly independent vectors over R is going to be 2e1 up to 2ed. And why is that? That's because the L2 norm of this vector 1, 1 is going to be equal to square root of d, which is going to be greater than or equal to 2 whenever d is greater than 5. Sorry, it's greater than 2 whenever d is greater than 5, like greater than or equal to 5. And therefore, the shortest linearly independent vectors are going to be the vectors that have, which are 2e1 up to 2ed, that they all have only even coordinates. But clearly, this is not going to be a basis of lambda over z, because, for example, this vector here of 1, 1, 1, 1, 1 cannot be spanned over z by vectors that all have even coordinates only. So this is one reason why some of these methods will not be able to be translated to the real case. Okay, so now let's explain a little bit more about the elements of the proof. So one of the main elements of the proof is this decomposition theorem that we showed, which is also not true in the real case, which is that for every lattice lambda, we can find some isometry, that is some matrix U, which is in SLDO, such that U times lambda is going to be a diagonal matrix times RD, where on the diagonal, we have elements of the form x to the power of log the first successive minima up to x to the power of log the last successive minima. So this is saying that up to isometry, we have a very, very simple form of this lattice. Now we're ready to try the proof out for the case that C is going to be equal to OD. For other cases, I'll leave it for the listener or reader of this of these slides as an exercise if you have energy to do it. So firstly, we remark that the covering radius with respect to OD is going to be equal to the covering radius with respect to the infinity norm. And also, we notice that since this infinity norm is invariant under SLDO, and why is that? That's because this is an isometry. Then by the previous theorem that we had here, since this is going to be an SLDO, then it will suffice to prove it only for these type of lattices. So it will suffice to prove that the covering radius with respect to OD of this lattice here is going to be exactly this here. Now, let's prove a double-sided inequality. So on the one hand, I'm going to choose my shift to be this vector here, which is going to be ED times x to the power of log q of lambda d minus 1. That is, I took this last vector here and I multiplied it by x minus 1. Now we notice that the point which is closest to this vector with respect to the infinity norm in this lattice is going to be 0. And this is not very difficult to see. And therefore, we get exactly this here. That we get exactly that for this specific shift, we get 1 over q times lambda d. And therefore, the covering radius with respect to OD of lambda should be at least 1 over q times lambda d of lambda. On the other hand, let's do this. Let me take some arbitrary vector, and I'm going to write it as a linear combination of these columns here. So I took some vector, and I'm going to write it as a linear combination of these columns, which are going to be x to the power of log q of lambda I times ei. And the coefficients are alpha I, where alpha I are some elements in k tilde. Now, I notice, firstly, that if I subtract from all of these, this exact same vector, only I change the coefficients, and instead of taking alpha I take the polynomial part of alpha I. That is, if I take, for example, alpha to be the sum of n equals to negative infinity up to some big N of an times x to the n, then I'm going to define this polynomial part of alpha to just be the sum when I take n equals 0 to n of an times x to the n. Now we realize that if we subtract this here, then one of the things that happens is that we're going to get this sum here in this form, I equals 1 to d of alpha I times x to the power of log q of lambda I lambda times ei. Now, one thing that happens in this field is that we have the ultrametric property, which I'm going to write here in a different color. So the ultrametric property says the following, that if you have two vectors, u and v, then the infinity norm of u plus v is going to be less than or equal to the maximum of u and v. And this is also true, and this is true also for the absolute values. So now we use that to say that this thing here is going to be less than or equal to the maximum of I of this alpha I times this thing here, which has norm lambda I of lambda. Now notice that the non-polynomial part can have norm at most q to the minus 1. And then these successive minima, we're going to take the largest one, which is lambda d of lambda. So we get that this maximum here is going to be at most q to the minus 1 times lambda d of lambda. So this gives us that the covering, that for every lattice, for every vector v, we can find that we can approximate it with respect to the infinity norm up to q to the minus 1 lambda d. In other words, the covering radius is at most 1 over q times lambda d of lambda. And this double-sided inequality gives us an equality. I think this is a good time to stop for questions. So does anyone have any questions? Okay, so if there are no questions, I'll continue. And I'd like to also discuss Minkowski's theorem in positive characteristic. And this has to do with what we showed previously, because we're going to apply this to compute the Minkowski's function, or at least to bound it in some way. So in this situation, the Minkowski function is going to be the exact same thing. We take, in this case, n of v is going to be the product of the coordinates of v in absolute value, and we simply define the Minkowski function to be the covering radius with respect to n, which I just rewrote here the definition of it. So now let's talk about some properties of mu. This is just a sanity check of ours, so that we make sure that mu has the same type of properties as in the real case, and therefore it is something interesting to study. So some of the properties of mu is that one thing that we could see is that mu is invariant under the group of diagonal matrices with determinant of absolute value 1, And why is that? That's because n is invariant under this function as well. Moreover, one can compute that mu of the standard lattice Rd can be obtained by taking the shift being 1 over x, 1 over x, 1 over x, 1 over x. And in this case, we obtain that we get q to the minus d. Those of you who are extra ambitious today can verify this computation or do it themselves. So these two properties together may give us a good idea or a good guess as to what should the upper bound of mu be. And indeed, this isn't the real upper bound. So one of the theorems that I proved was that for every dimension d, the upper bound of mu is going to be q to the minus d. Now we can ask, okay, that's part one of Minkowski's conjecture. In the real case, we had a second part, which was about uniqueness. And unlike the real case, we were able to show that we don't have uniqueness and something even stronger. We know that the lattice Rd has a divergent a orbit that it eventually goes to infinity here. That is, we take the function a goes to a times Rd, then this function is going to be proper. And now, or another way of saying is that eventually leaves every single compact set. And now we say that we have the following. Not only is it that we can find lattices that are not in ARD that have this upper bound, rather we are able to find infinitely many distinct compact A orbits, A lambda, such that mu of lambda is equal to q to the minus d. Now let's ask, how did we do this? So let me give an idea of how we did this. So the way that we did it was, firstly, we constructed a sequence of distinct compact A orbits, which have some effective version of escape of mass. I'll explain this shortly. So we know that if A lambda is a compact orbit, then there exists a unique invariant probability measure, which we call it mu of A lambda. And in this case, we constructed a bunch of these compact A orbits and a bunch of these and then therefore they have a bunch of these measures, and we were able to show that for this specific sequence that we constructed, these measures must converge to the zero measure. Not only that, we were able to show this at a specific rate, and this rate enabled us to prove that there is some subsequence of these orbits that satisfies that mu of lambda n converges to q to the minus d. But wait, 1 minute. Mu of lambda n, this is going to be, so lambda n is some function. So mu of lambda n is some function which involves norms, right? It involves absolute values. Now notice that it's a product of absolute values, and an absolute value in our space could only obtain either the value 0 or the value q to the minus k for some k which is going to be in z. Therefore, saying that mu of lambda n converges to q to the minus d means that it's like saying that for any large enough n, mu of lambda n is equal to q to the minus d. And this has to do with our unique geometry that I showed earlier, that you could only converge to points which are non-zero along the same sphere. So are there any questions about this idea or about this theorem?
Well, I actually have a question about part one. I just don't understand. So RD is the standard lattice.
Yes, yes.
And what do you mean by lambda is inside RD? Lambda is also a lattice. So what is lambda?
Oh, yikes. Yeah. This is a typo. This is actually supposed to be LD. Thank you.
Oh, the space of lattices. So okay.
Yes,
okay.
yes, this is the space of lattices. That's a typo. Thank you.
Now it makes sense. Sorry.
Yes, yes. Okay. So now that we have an idea on how to prove the second part, let me explain how we proved the first part. So we did this in 3 different steps. The first step is we showed that there is a set of lattices called the well-rounded lattices, which satisfy that the covering radius of these well-rounded lattices is going to be q to the minus 1. Let me write this explicitly. This means that if we take the set of these such that the maximal coordinate is at most q to the minus 1 and translate it along all the lattice points of lambda, then we obtain the entire space. We cover the entire space. Now, this implies that every well-rounded lattice lambda will satisfy that mu of lambda is less than or equal to k to the minus d, to q to the minus d. And why is that? That is because we notice that this set up here, if the maximal coordinate of v is going to be at most q to the minus 1, then the product of coordinates is going to be at most q to the minus d. So any lattice that satisfies this first equation must satisfy the second equation here. And this here implies that mu of lambda is going to be less than or equal to q to the minus d for well-rounded lattices. Now, we're not yet done because we only proved this for well-rounded lattices. For the third part, we need another part, which is we now show that every A orbit must intersect the set of well-rounded lattices. And recall that since mu is A invariant, then we obtain that every lattice must satisfy that mu of lambda is at most q to the minus d. So this is a lot of steps. I'd like to draw them. At least I'd like to draw how 1 implies 2. So to see how 1 implies 2, we notice that this purple square here is a set of v's such that the maximal coordinate of v is at most q to the minus 1. This is going to be contained in this blue star, which is a set of v's such that the product of the coordinates is at most q to the minus d. So if I can move this purple square along these pink lattice points and cover the entire space, then if I take a larger set, for instance, this blue star, I should be able to do the same. So now let's move on to what was our major player here, which is the well-rounded lattices. We say in this case that a lattice lambda is well-rounded if all of the successive minima are equal to one another, and they are going to be equal to 1 due to Minkowski's second theorem in this setting. We denote this set by WRD. Now, one corollary that we had, as we recall, we had this theorem. So we have this theorem here that says that the covering radius of some lattice lambda with respect to a convex body C, let's do it as OD, is going to be equal to 1 over q times the last successive minima of lambda. Now, in this case, since the last successive minima is 1, then the covering radius with respect to OD of every well-rounded lattice is going to be 1 over q. This implies, obviously, that mu of lambda is q to the minus d from our previous picture. So now I have 2 more parts that I would like to show. One part is going to be the proof of how every A orbit intersects the well-rounded lattices, and that if I have time, I'll do that after a short break for experts. But before that, I would like to show an application of the fact that every well-rounded lattice that every A orbit intersects a set of well-rounded lattices. And this has to do with the Mordell function. So now we say that a box, that's going to be a set of this form. It's going to be a product of a bunch of balls, or you could view it as a set of the form V in K tilde, such that Vi is going to be at most Q to the power of Ri, is admissible for some lattice lambda if B only intersects lambda at 0. That is, B contains no non-zero lattice points of lambda. Now, we define the kappa of lambda to be the supremum of the volume of admissible boxes for lambda. So let's say some easy properties. Firstly, kappa is A invariant. Why is that? That is because the volume of a box is not affected if we multiply this box by some A, for example, or if we multiply lambda by some diagonal matrix that has determinant of absolute value 1. That's one way to view it. And moreover, this is the property I won't go into. Kappa is lower semi-continuous, and also recall that A acts ergodically on the space of unimodular lattices. So by ergodicity, it has a generic value, and due to this lower semi-continuity, this generic value is going to be its upper bound. And now we can ask, what can be the upper bound of this kappa. Another thing that we could see is that kappa of the standard lattice, RD, is q to the minus d. And why is that? That is because the box, which is given by B0, q to the minus 1, that is going to be the set of all vectors v, which are going to be less than or equal to q to the minus 1, only does not contain any non-zero lattice points of RD. And on the other hand, if we increase this box slightly in any direction, then it will have to contain some non-zero lattice point. And another thing is that by Minkowski's convex body theorem in this setting, that's a theorem that connects between the determinant of a lattice and the number, and basically how large must a set be in order to contain non-zero lattice points of it. Then the upper bound is going to be q to the minus d. That basically it says that if you have a lattice that's unimodular and you have any convex set which has volume at least 1, then it must contain a non-zero lattice point. Okay, so now we have all of this. One of the things that I was able to prove using the fact that the well-rounded lattices they intersect every A orbit is that kappa is a trivial function. That is, for every lambda in LD, kappa of lambda is equal to q to the minus d. So let's see the proof. So firstly, notice that if we take some lambda, then A lambda must contain a well-rounded lattice. And since kappa is A invariant, it will suffice to prove this lemma only for lambda which are well-rounded. So now, if we take some well-rounded lambda, then we know that lambda 1 of lambda is going to be equal to 1. How can we reinterpret this? We can reinterpret this by saying that lambda does not intersect the ball of radius q to the minus 1 with respect to the infinity norm. And therefore, this ball is going to be admissible for lambda. So we obtain that kappa of lambda must be at least the volume of this ball, which is q to the minus d. Since the volume of a ball is simply going to be its radius to the power of d in this case, or the volume of a box is going to be the product of all of these q to the ri's. So this gives us, due to the upper bound, that kappa of lambda must be q to the minus d for every single lambda in LD. Are there any questions about this part? Okay. I will say that this is very, very different from the real case, in which values of kappa, they actually correspond to very rich structure of the A orbits. In other words, for example, if you have a compact orbit, then it will not obtain the upper bound, for instance, in certain cases, and that their kappa can obtain very many different values in the real setting. And this is the result by Shapira and Weiss from 2015. And it's very, very different from the positive characteristic setting. Another way to say this is that Shapira and Weiss, they show that this function from geometry of numbers kappa, it corresponds in a very, very deep manner to the dynamics of A, but in the positive characteristic setting, that is not the case at all. Rather, it's trivial. So now I'll ask a few questions that I have been interested in, and if anybody from the audience may have some input on these or any ideas, I would really love to hear them. So one question is, what about mu? We found that kappa is generic. What should be the lower bound or the generic value of mu in this case? Now, another thing is that we know that in dimension 2, mu is going to be the trivial function. That is, for every lambda, mu is equal to q to the minus 2, just like kappa in every dimension. Now we can ask, is this also true in dimension D? I will say that in dimension 3, I've been able to run some computer simulations to compute mu, and due to some of my calculations, it appears that it could possibly be trivial in dimension 3, but again, since these are just computations for finitely many lattices, it may not be enough to say that it is trivial in dimension 3, and I may have not gone deep enough. Now, another question is what happens to other covering radii in positive characteristic? In particular, we took mu because it was invariant under the whole diagonal group. So what happens if we take, for instance, covering radii, which are invariant, let's say, under some fixed one parameter flow? How does this correspond to the action and the dynamics of this group, for example? So these are some other questions that are in general interesting in this sense. And we could ask, for instance, if we take an ergodic flow, then how can we use the dynamics to study the covering radius in this sense as well? So now that I've asked some of my questions about this, does the audience have any questions?
Yeah, I have a question about your question 4.
Please.
So it's a nice question, but what about
yes.
Well, can you say something over the real numbers?
Over the real numbers, I actually don't know what can be said there, but that's another good question. Like, for instance, I would say if you take, for example, the Diophantine-Worst shift, then it turns out that in positive characteristic that it's almost a covering radius is trivial, and in the real case, I understood that it may not be.
Wait, what are you taking now? So
like, for example, if you take, this is almost a covering radius. You take, for example, the supremum on gammas over, like, let's say the infimums on n of n times, let's do it in this dimension, n theta plus gamma. And let's say n is non-zero. So this is almost a covering radius. This is very, very similar to the Minkowski function in dimension 2. And this one is actually trivial. And you can take this in higher dimensions as well, and then it would be invariant under a one parameter flow.
Okay, so it's right. It's some kind of so in R3 it would be some kind of a hyperboloid of revolution.
Yes, yes, yes. This is very similar to the Minkowski function, but not exactly, because in the Minkowski function you have this shift here with n, and you can take n to be 0. So it's almost a covering radius.
Mm-hmm. Yes,
but I don't know of any results in the real case, and this is definitely something worth investigating.
Well, then probably badly approximable vectors create the situation where you have infinite non-zero.
Yes, yes, yes. For badly approximable, yes.
Mm-hmm.
But that's again almost a covering radius, because the n because you want the n to be non-zero, and you don't have the shift on the n court on the part where you have only n.
Mm-hmm.
Does anyone else have any questions?
But if you add the shift to this part, then what is happening?
Yes, then you get exactly the Minkowski function, because this is what I had in one of the previous slides. Because then, let me try to go back to that slide. Yes, I think it was.
But is it dimension 2 or higher dimensions?
In every dimension, you get exactly the Minkowski function if you add the shift to that part. Yeah, I think it was over here. No. Yeah, this was it. Yeah, see, you have exactly, you get in every dimension, if you add this shift here, then it's exactly the Minkowski function.
Okay, but this is about full diagonal group, but I thought we were talking about one parameter group. So what if you take the last line, instead of the product of n theta plus alpha and n theta plus beta, you replace the product with the maximum squared.
With the maximum squared. About that, I think that I don't know of any results. I think that Uri may have had a result which is similar to this, but it talks about the possible values the grids obtain and not the supremum value. Mm-hmm. That is, you simply, instead of saying what is the worst possible value, you look at the possible set of values. You say, I'm going to look at, instead of this, I'm going to say, let's look at all of these values where I take gamma, alpha, beta, and gamma to be some values in R. So I think that he has a result about these, but not about the worst shift when you took that function in particular. Okay, interesting. I believe it's called Grids with Dense Values, that paper. I'm not sure, but I think that that's a paper.
Yeah, well, but it's still about the product?
Not necessarily this product. It can also be about, for example, taking the first coordinate, v1 squared times v2 or something like let's say v1 squared times the maximum of v2, v3.
Mm-hmm.
I think that he deals with those as well. I do remember that there is a mistake in that paper, so I'm not sure if the result there holds for these, but I think it may.
Okay. Well, anyway, anybody else wants to ask a question? Maybe before that, we should really thank the speaker for a great presentation with a virtual round of applause. Or,
thank you.
Some applause like
I
this.
actually have a second part, so we can also thank after that.
Okay. All right. So then go on. Sorry.
So yes, I do have a second part, but I think it's a good time for a recess right now.
Yeah, I guess, I mean, people who can step out, who want to step out, can step out. If anybody wants to use this recess to ask questions, please do. So what is the second part about?
Oh, the second part is to prove that every A orbit intersects a set of well-rounded lattices. It's only 6 or so slides, but it's a bit technical, so I was not sure if I would have time.
Yeah, I mean, I'm all for listening to it.
Okay, great. So I suppose we can do a recess until about 20 minutes past, and then after I can come back for the second part.
You mean
Or,
you want to take a break in 5 minutes?
Yeah.
5 minutes?
Yeah, I suppose so. I suppose so. Like I can do a little bit less, unless if some people want to have some more.
I don't know. Maybe. Yeah, I would say we're probably ready for the second part.
Okay, great. I am. So let's do this. Okay. So I can do the second part already. So great. So for the second part, let me just open this up. Okay, great. So for the second part, I'm going to show that the space of well-rounded lattices, it intersects every single A orbit. So let's do this. So the way that we do it is the following. We're going to first reinterpret this in terms of flags. So a flag is going to be a sequence of subspaces which are contained one in another. And maybe before I should explain this, I'll say that a lot of these ideas are due to Omri Solan's paper, which proves this exact result in the real case, and also due to many conversations I had with Omri Solan about this positive characteristic setting and how to do this. So I'm indebted to him for this proof. So now, we first reinterpret this in the language of flags. So a flag is just basically a bunch of subspaces which are contained one in another. And now we associate with this flag or with a subspace V, which is going to be spanned by V1 up to Vk, its determinant, which is going to be the norm of this wedge product, V1 wedge up to wedge Vk. So this is going to be a bit of technical language that's going to help us understand how to prove this. Now, let me define a specific flag, which is a Minkowski flag. So the way that we can view this is we have some norm, any norm, which we denote in this manner, and we have some lattice, and we define the Minkowski flag of lambda to be simply, with respect to this norm, to be simply the flag where all the subspaces are going to be the span of lambda intersected with the ball around of radius lambda 1 of lambda up to the radius lambda d of lambda. So let me give a quick example. let's do this as a sanity check. So if we take, for example, this lattice here, which is going to be, let's take, I'm going to write it up above. So let's take, for example, the lattice lambda, which is going to be, for example, x to the power of r1 up to x to the power of rd times rd. Then we can see that the successive minima are going to be q to the power of r1 up to q to the power of rd. So our flag in this case is going to be 0, which is going to be contained in the span of b of lambda, the ball of radius lambda 1 intersected with lambda, which contains only one vector, that is the span of x to the r1 e1, which is contained in the span of x to the r1 e1, x to the r2 e2, up to the span here, it's going to be contained in the span of x to the r1 e1 up to x to the rd ed, which is exactly equal to k tilde to the d. So that's one example of seeing this Minkowski flag. I took a very easy example, but you could do this for any lattice. So now let's reinterpret this entire thing in terms of this Minkowski flag. So we can say that if we have a lattice lambda, a lambda intersects a set of well-rounded lattices if and only if there exists some a such that the Minkowski flag is trivial. Why is that? Because what I want to say is this: if lambda 1 is equal to lambda d equal to 1, then what do we get? We can say that the ball of radius q to the power of r intersected with lambda is going to be one of two things. It's going to either be 0 if r is less than 0. That's because any ball of radius q to the minus something does not contain non-zero points of lambda. Or if r is going to be at least 0, that is, this is a ball of radius 1 intersected with lambda, then we get k tilde to the d, because this is going to contain e1 up to ed. So that's one way of reinterpreting this in terms of these flags. So now what I want to do is I want to, instead of acting on lambda with this a, I want to act on these norms with this diagonal group A. So I'm going to define new norms which are induced by these a's. So instead of viewing a as some element of the diagonal group, I'm going to define a, which is some element of rd, such that the sum of the coordinates is 0. And I'm going to define norm with respect to this a in the following manner. The norm of some v in k tilde to the d with respect to a is going to be the q to the power of the maximum of ai plus log of vi in absolute value. Now, we notice that if a is going to be in z0d, that is zd intersected with r0d, then the norm of v with respect to a is simply going to be the norm of x to the a v with respect to the infinity norm, where x to the a is simply going to be this diagonal matrix with diagonals x to the a1 up to x to the ad. And this is not too difficult to see. So now let's explain how can we reinterpret this differently. So one of the things that, so we had these new norms here, and now let's reinterpret this. So we had this reinterpretation here, which is that a lambda intersected with the well-rounded lattices is non-trivial. Now we want some a in z0d such that the Minkowski flag with respect to this norm here, with this a norm, is going to be trivial. Now, one of the theorems that I was able to prove is that if for every lambda, we can find some a in r0d, such that this Minkowski flag is going to be trivial. And this is actually a positive characteristic analog of the main result of Solan's paper. So now we can ask, how do we make this r0d, which is almost perfect, some a in z0d? So I'll show how we prove this, and I'll use some lemma. So the lemma that we use is that if we have the Minkowski flag of lambda, this is the wrong type of lambda here, with respect to some A norm is trivial, then this A norm is going to be up to a constant. It's going to be a norm of a convex body of this form here. That is, we can find a convex body B with respect to this A norm 0C, such that this norm is going to be like that. So now let's show the proof. Given this lemma and this theorem, how do we prove this? So firstly, let's show why A lambda must contain a well-rounded lattice. So we can assume that lambda is not well-rounded. Otherwise, this proof is trivial because then A lambda will contain lambda, which is well-rounded. So now we want to show that there is some A in Z0D such that the Minkowski flag with respect to this A norm is trivial. Okay, so by the theorem that we showed earlier, there is some A in R0D such that this Minkowski flag is trivial. Now, I'm going to write this A in the form of A1 plus A2, where A1 is some element of Z0D, and A2 has maximal coordinate, which is less than 1. Now I can assume that A1 is going to be 0, because otherwise I'm going to replace this lattice lambda with the lattice x to the power of A1, which is also a lattice in LD, because x to the power of A1 is going to have things of the form x to the power of some element in Z on the diagonal. So that's also going to be a lattice. And also, let's assume that, and then if A1 is 0, then A2 is going to be non-zero, because recall that lambda itself is not going to be well-rounded. So if A2 and A1 were 0, then lambda would have to be well-rounded. So now, by Minkowski's second theorem for convex bodies and the previous lemma, we would get that, that if we take the successive minima with respect to these special norms here of this lambda, we would get 1. And why is that? That's simply because we have, if we take the successive minima with respect to a convex body, then we would get this, then we would have some element which relates to the volume of the convex body, but because A relates, this norm with respect to A relates to the norm with respect to the convex body, then it cancels out. And then that's why we get this 1 here. And now what we would get is that if indeed this was trivial, this Minkowski flag was trivial, then we would have to get that all of these would have to be equal one to another. But then they would all have to be equal to 1 because of the previous equation. Now, since by assumption our lambda is not going to be well-rounded, then we can find some vector such that its infinity norm is less than 1. Because if it were well-rounded, then the first successive minima would be 1, and that is the largest possible first successive minima that we could have due to Minkowski's second theorem. So now we would get, let's recall what this is. This VA is going to be equal to Q to the power of the maximum over I of the log with respect to Q of VI plus AI. Now, notice that the log with respect to, let's do it in this color. So every one of these guys here, log with respect to Q of VI, every one of these is going to be less than 0 because the infinity norm of Q is less than 1. And all of these AIs here are going to be less than 1. But moreover, recall that V is going to be a vector in K tilde, and therefore the log with respect to Q of V is going to have to be, this is with respect to the norm, is going to have to be less than -1. So all of this here, this plus this, is going to be less than 0. So we have Q to the power of something which is less than 0, and therefore this here would all have to be less than 1. And that is a contradiction to the fact that this would have, that if we take this here with respect to the A norm, then we would get something which is trivial. So therefore, we obtain that we had to have, or that we cannot have the case where A1 is 0 and A2 is going to be non-zero. So in any case, A2 must be 0 in this case, at least, or we can say that if indeed we have some A which satisfies this, then we could also take A2 to be 0. So are there any questions about this proof? Okay, so I think this is a good time to stop, and that's all I have to say anyway. So thank you very much for listening.
Okay, thank you for the talk. Let's now we can do the uploading, either loud or virtual. Any questions to the speaker? We still have time for a quick round of questions. Okay. All right, so thanks, Noy. So then I guess it's time for me to stop recording. And thank you all for coming, and thanks to the speaker again.